All right, so welcome to our latest child-adult health rounds, and I'm really excited about today's presentation. We have Catherine Goudie and George Thanassoulis, and like I was saying to both of them, they're like the golden children of CORE. Is Catherine, I don't know, for those who don't know her yet, you will soon. She's a pediatric oncologist and researcher, and she came to us really less than a year ago, a few months ago, having done a fellowship at Sick Kids. And shortly before she was hired, she was told to go get an FRQS award. So she dutifully did that within a 2-week time frame. And then, of course, this last round at CIHR, she got an operating grant. So if we all follow a trajectory like that consistently, success is guaranteed. And George Thanassoulis, I'm sure you all know him. He's famous now. But George is a cardiologist and epidemiologist who, routinely publishes in Circulation and the like, and holds several grants from CIHR. And he's interesting because, like Catherine, he does analyses using large, genomic data sets. But he also writes papers based on what he's written on the back of a napkin. And so he sort of puts together these logical frameworks and then gets published in huge journals. So I'm really excited to learn from both of them. What's unifying here, I think, is the interest in genomics, looking at different issues, but I think we'll see some parallels and hopefully we'll all learn something.
Hi, everyone. Does that work? Okay. Thanks for the introduction, and thank you for giving me the opportunity to present here today. So I do want to say I did get a lot of help for that FRQS in such a short period of time, but it shows that really I was not planning on starting my career off like this, and if you talked to me 2 years ago, I was planning on being a clinician at that point in time. So everything can change even relatively close to the end of training. So today I'm very pleased and happy to talk to you about a subject that's been a big interest of mine for a very long time, which are cancer predisposition syndromes which present in pediatrics. Okay, so when a child is diagnosed with cancer, one of the first questions that comes to a family's mind is, why did this happen to us? Why our child? Why our family? And very rapidly, the question about other family members, are other family members at risk? In 10% of cases, I don't know if I have to point somewhere. No, it should work. Okay. So in 10% of pediatric cases, the childhood cancer is associated to an underlying cancer predisposition syndrome, which is a genetic condition that increases your risk of developing one or multiple cancers throughout lifetime. Some children develop many cancers. I've followed a child who was now, well, not a child anymore, 16, and she had 8 cancers already. And she was going to school and doing actually quite well. But this is something that is probably more prevalent in pediatric age than in adult age, even if we hear more about cancer predisposition syndromes in adults with breast cancer and hereditary components to that. So 10% of childhood cancers are associated to cancer predisposition syndromes, and there are over 125 different cancer predisposition syndromes that have been associated to pediatric cancer. It's really important to be able to identify these cancer predisposition syndromes early because it may affect directly how you manage the child's cancer. It may also permit us to incorporate cancer surveillance measures, not to prevent a cancer from happening, because that often can't be done, but at least to try to catch them earlier so that we can decrease the morbidity of the treatments and increase survival. And also for at-risk family members to offer them genetic counseling. a minority of children have cancer predisposition syndrome in their families, or known cancer predisposition syndromes in their families, or even family histories of cancer. And do you guys know why that is? Lara, you cannot answer this question. The reason is children are really young. So they're young. They have young parents. They have young family members who often didn't have time to develop any type of cancer that would have made you suspicious in that family. And if you talk about genetics to any physician that doesn't necessarily have a genetic background, they right away jump to family histories. And if there's no family history, they kind of stop their questionnaire right there. But there's a whole bunch of different things in the presentation of a childhood cancer that could make you think about a cancer predisposition syndrome. There's a small study that I had done during my fellowship at Sick Kids looking at 172 patients who were diagnosed with a cancer in pediatric age and a cancer predisposition syndrome over an 18-year period. And the goal was just to see what was diagnosed first and how long did it take to actually identify the syndrome in that child. And what we can see is that 80% of children, or almost 80% of them, had their cancer before being identified with their syndrome, and that there was a mean time frame of 6 years between the initial cancer diagnosis and the syndrome diagnosis. And this is at Sick Kids, where they have the largest pediatric cancer genetics program, and they treat 25% of the Canadian population. So you'd expect it to be good in that institution. And also what we see, and this has been seen in a few studies, is that about 30% of children have a family history of cancer. So you are a general physician. You see a child with a cancer, any type of cancer. Here I took Wilms tumor as my example. And you're wondering if you should be referring this child for an evaluation in genetics. You have essentially two options right now. Either you go with your experience, you call a friend that has more experience than you PubMed, and you try to identify if that child may be a candidate for genetic testing. And then you hope that you have genetic testing for pediatrics in your center that will see a child rapidly with cancer. Or you can adopt this new tendency, which is to test everyone for everything, which we're calling universal genetic testing. And in pediatric oncology, there are more and more initiatives that are testing consecutive children with very, very large panels to see if these children either have genetic alterations in their tumors that could be actionable, or germline mutations that would orient us towards a cancer predisposition syndrome. But what if you could click on a cancer type, any type of cancer, and you on an app that would ask you a few yes/no questions that you can directly answer at diagnosis, and it would tell you if you need to refer the patient to genetics, yes or no. And on top of that, it would tell you why you're referring to genetics. So that's MIPOGG. That is the McGill Interactive Pediatric OncoGenetic Guidelines. And that is the platform that I've been working on in very different ways, and is the basis of the research program that I have here. So the MIPOGG is an eHealth tool that is copyrighted at McGill, and in which we are currently developing the software for it, but in parallel to that, we're looking at the performance of all of these different algorithms. So this is just, it's actually not the real picture of the software, but it kind of gives you an idea. It's going to be a website and an app, and it really answers the question, which child with cancer should be referred to genetic service? It's an app that is built for healthcare professionals, so not for parents of children or for people that don't have cancer. The entry point to this app is having a cancer, because the first question in the app is to click on a cancer type. So it's not made for the whole population. It's very specialized, if you want. This tool currently contains 140 tumor-specific algorithms that took about 5 years to build. which I'll go through with you a little bit the methods regarding that. But every childhood cancer in the International Childhood Cancer Classification, and for the brain tumors, which are classified a little bit differently in pediatrics, we're using the WHO classification, and we also have some benign tumors in there, for example, certain skin tumors, and even certain benign brain tumors that don't necessarily get to oncology, but get to other services in the hospitals, but that are highly specific for cancer predisposition syndrome. So it's really got the whole array of different types of benign and malignant tumors that we see in pediatrics. And it doesn't tell you, it doesn't do genetic testing for you, and that's something that's very important. It just tells you, it streamlines genetic referrals. So the first step of this project, which started a good 5 years ago now, was first of all to identify as many motivated medical trainees, staff, genetic counselors, clinician researchers who wanted to participate in the development of these algorithms. And we made a standardized method in terms of literature review and how to identify keywords to search for all of the different predisposition syndromes that are associated to a cancer, and then to identify all of the different phenotypic features that you can see in those syndromes. And then the goal was to put all of that together like a big puzzle and identify the criteria that are have a highest sensitivity, that are most valuable for certain syndromes, and avoid repetition between the questions. So each algorithm, and this is just an example of the workflow for one of the 140 tumor algorithms, which is the Wilms tumor one. And the goal is to make some tumor-specific questions, and then what we have also a set of universal criteria, which are questions that, independently of the tumor type, if you say yes to one of those questions, you should be sent to genetics. So we have 6 tumor-specific, 6 universal criteria, and the physician will only access those specific questions if you've answered no to all of the tumor-specific criteria. And the goal is to make it as short as possible for physicians, because if it's too long, physicians will not look at it. So that's the way that we built all of the algorithms. Once they were all built, we had them evaluated by different health professionals, either clinical or in research, that had expertise in that specific tumor type, to get a critical review of those algorithms. But still, at that point, they weren't tested on anyone. So we wanted to test their performance before making this public. So we did some preliminary performance studies at SickKids during my fellowship there, where we looked at 1,750 consecutive pediatric cases of cancer, independently of if they had a syndrome or not. And we applied, we ran every single case through the appropriate MIPOGG algorithm. And we wanted to see what would be the MIPOGG referral rate, because if the algorithm is referring everyone to genetics, then the algorithm isn't good. If the algorithm is not referring enough people, then it may not be sensitive enough. So one of the first steps was just to see, in that group of people, is it feasible even to apply this algorithm? And we also looked at the level of agreement between the MIPOGG response and what physicians actually did in real life. So this is an example of one of the, well, not decision trees, but outcomes, I guess, for one tumor type, which is osteosarcoma, which is the most common sarcoma in pediatrics, where we had 128 osteosarcoma cases. And if we would have applied the MIPOGG algorithm to each of those cases, we would have referred 48, which looks like a big number for you guys in terms of referral rate. But this is, we have to remember, as opposed to wanting to send everyone to genetics, which is likely not feasible, even in the largest of centers in Canada. But of those 48 people that MIPOGG would have recommended, the 7 patients that actually had a cancer predisposition that were confirmed were in that group. So the positive predictive value of that MIPOGG yes, independently of the of what else in terms of family history and things like that in that patient, would have identified all of those that physicians would have identified. So it does give us a little bit of information, but it's not a good performance study. It's very preliminary. So then we wanted to know, is MIPOGG, if we add MIPOGG to physician practice, is that better or at least as good as what physicians have been doing? So we've identified about 400 children in Canada right now in 12 different centers who have both a cancer and a cancer predisposition syndrome. That predisposition syndrome was identified because a physician thought about it. So these are children, it's a biased population because they had to have a lot of features for the physician to identify it and then be confirmed to have a syndrome. But still, it's important to run all of those kids retrospectively through the tool to make sure that the tool would do no harm and that would catch all of the kids that physicians would have at least caught. So that doesn't tell us if MIPOGG is better. It just tells us if MIPOGG isn't doing harm. But in those 400 patients, there's about 50 of them, even I maybe go up to 75 actually, that have had 2 cancers before the physician sent them to genetics. So now we're going to check if MIPOGG would have identified those kids at the first cancer. And then it starts telling us, okay, can MIPOGG be maybe a little faster than physicians, maybe a little bit better if we used it. But still, we're only looking at the cancer predisposition positive group. So we can't measure we can't look at the measurement properties of the tool correctly with that type of method. But we're getting a little bit closer with this. Sorry. So let's say, it's really exciting. So let's say we were able to actually know if those children didn't have a cancer predisposition syndrome. So right now we have the luxury of having a lot of different initiatives in the world that are doing very large germline panels on children with cancer. And so if you don't find anything currently, that's what we're considering a gold standard in terms of not having a cancer predisposition syndrome. So while it's not perfect, it's the best we have. So we were able to link with many different initiatives and gathering about 850 children with cancer who have also had comprehensive germline sequencing. And we are currently being blinded to all the results of the genetic sequencing, and we're running every child through MIPOGG and identifying which ones MIPOGG would have sent and would have not sent, and then getting unblinded to those genetic results and seeing how good MIPOGG actually works. And the goal of that is really not how good does it identify a kid, but how good does it identify a kid that does not have a syndrome. Because MIPOGG is essentially a screening tool. And we want that negative predictive value, so when MIPOGG says no, to be as high as possible to reassure a doctor that is not sending the child to genetics. We do want some high sensitivity, which kind of goes with the negative predictive value, but we essentially want, when MIPOGG says no, that you can sit down and rest assured. And the reason for that is that if you get out of Montreal, and if you get out of Toronto, and if you go anywhere else, genetic testing is not easily accessible. So no matter how hard we're working on trying to do genetic testing on everyone as part of big studies, that's not feasible in the majority of places in the world. So it's very important to identify a strategy that would pick out the proper kids that really need to go. So this is currently ongoing and a big part of what we're doing right now. And this is a part of the operating grant that we have. Another thing is that MIPOGG is not, this strategy of picking out kids is not accepted by everyone, meaning it kind of knocks heads with these studies that want to test everyone and wants to show that there's a higher cost effectiveness if you do germline sequencing or large panels on kids, because you're missing less kids and they get proper surveillance and you find the cancer earlier and it's less expensive at the end. But we actually don't have any type of study that does compare these strategies. So what we're doing is taking many different scenarios, pediatric cancer scenarios, in which we are looking at what physicians would have done, what MIPOGG would have done, and what universal testing would have done in terms of identification of cancer predisposition and the ultimate actions that are taken after that. So it's not a cost-effectiveness study to look specifically at MIPOGG, but it's to look at the 3 genetic referral strategies that we have currently in pediatric oncology. And this is done with Nandini's group here, but also with Dr. Petros Peklivanoglu's group at Sick Kids, who is a health economist there that specializes in pediatric oncology. So as you can see, MIPOGG was a very simple. This is just a slide showing the different elements that we're looking at in the cost-effectiveness study, and we've divided it into different modules depending on the timing of the course of the life of a child who develops cancer, who becomes a survivor, and who could develop second cancers as time goes on. But as you can see, this project was a simple idea in the past, and it was just, let's make a list of the different kids that need to go to genetics. It was supposed to be a paper list, and that was it. And then it turned out to be me presenting the list to a really, really smart geneticist, Dr. William Fowkes, who's a mentor for me. And he said, "Oh, Catherine, why is that one on the list? And why didn't you put rhabdomyosarcoma on the list?" And I was like, "Well, Will, if you put all the rhabdos on the list, you'll have way too many kids. You can't do it." And then we started trying to identify features for the different cancers. And one thing led to another, and it turned into an app. So, thank you. Thank you. That's it. Any questions? Yes.
Thank you. That was excellent. I have a question. So there are people who will refuse to go to genetics or that don't
Yes.
end up going to genetics, right?
Yes.
And so how do you handle these people in terms of looking at your, sensitivity, specificity? Because I saw when you presented the osteosarcoma,
Yes.
some went, but then some people did
Many
not go.
didn't. Many
Right.
didn't. So that is the reason why we're not going to put measurement properties on the tool based on the results of that study. But it did show us that a lot of kids who had the same features as some who were gone to genetics, and some kids had, for example, so one of the criteria in osteosarcoma is if you're aged less than 10, you should be sent to genetics. And the reason is there are a lot of either bone marrow failure syndromes or Li-Fraumeni syndrome, which are increased in that age group. And it probably surpasses a 10% likelihood of identifying a syndrome. But there are a whole bunch of kids who were less than 10 that were never sent to genetics. So why would one be sent and the other not? So a goal of those preliminary studies at Sick Kids was not to assess the proper performance of the tool, but was also to show physician practice. And to be able to have some preliminary data to feed into these other studies.
That was an excellent talk. Thank you very much. Initially, I thought you were going to sort of present this app approach for a single cancer, which would be a huge amount of work as you outlined, but that you scaled it up to all cancers is really amazing. But how do you handle, like, moving forward in terms of assessing the sensitivity, specificity? There's sort of a global level for this whole approach, but then each cancer must have its own performance. Yes. And then how do you do that multi-level adjustment? So you have to tune each one, I guess.
So it's a big question, and it's also another chapter in this story that's coming. For now, so the first goal is to look at it as a whole, as the tool, but then we do have different categories of tumors that we're able to lump together. So we're looking at MIPOGG, how good is it for brain tumors? How good is it for leukemias? How good is it? So we're able to make 4 or 5 classifications. We would like it to be at a granular level, but some tumors are extremely rare. And we will never have enough data for like an alveolar soft part sarcoma that we see, 3 in Canada per year if we're lucky or unlucky. Probably, I'd say unlucky in that case. But there are the big cancer types, we will be able to look at the measurement properties singularly, but many of them we have to lump together. The other thing is right now is MIPOGG, the outcome of MIPOGG is saying refer or don't refer, and it's linked to an educational module that links every single question to what syndrome we're looking for. So it tells the physician, okay, the kid is less than 10, he's got an osteosarcoma, we're thinking about this syndrome and this syndrome. If you've answered yes to that question also, we're thinking more about this syndrome. So every single algorithm has a table that explains exactly the rationale. But eventually, we would like to have the MIPOGG outcome say, yes, refer for syndrome X. Like we would like to be even more like determined to give a clear answer. But that comes with a lot of, you have to watch out a lot, because we don't want physicians to think that that's the only possibility and to forget everything else. So we're gonna, it's a very tricky project to do in terms of wording and how you present this to people.
One question. Could you give examples of how identifying the CPS,
Yeah.
like, is that actionable? Like what are some examples of, oh, this has meaningful impact to either the patient or the...
So that's an extremely good question, because there are, we talked about 125 different cancer predispositions. There are not 125 different syndromes that are, I'd say there's about 70 different syndromes that we play around with in this app. The reason is there are syndromes that it would lead to no action. So if we know that a specific syndrome you would identify just out of curiosity, we won't do that. Or we're not going to go look for a BRCA1, for example, a breast cancer gene, in a kid with a Wilms tumor. While that may become something later on if we have more data to support it, we don't want to send a child to genetics if the ultimate goal is to find something that you can't do anything about. So we've been picky about the different syndromes. But the actions, you have to think about them in a very large way, because an action could be changing your treatment for the cancer. An action could be starting surveillance. In leukemia, for example, if you have a syndrome that just increases your risk of leukemia, we actually don't have a proper surveillance for that. Because if you do a complete blood count in a child on that day, you can tell them they don't have leukemia on that day, but you can't, but in a week from now, it's not. So that hasn't been proven to be useful. So we look at that type of thing. But we also look at, so for example, a good example would be hepatoblastoma, liver cancer, and polyposis syndromes. So if you have hepatoblastoma, your risk of having a polyposis syndrome, familial adenomatous polyposis, is actually about 15%. So that, while it doesn't affect you right away if the child is 2, that parent, that 40-year-old parent, may need to be tested. And one of the determinants of health in children is also the health of their parent. So you have to look at it in different ways.
Thanks, Catherine. That was amazing. I wanted to ask you a little bit more about the universal screening.
Yes.
And also about the economic analysis part. So in the universal screening,
yeah,
is it like whole genome? They're getting everything?
So it depends on the study. The majority of people, they're doing whole exome, and they're picking out a specific cancer panel that is approximately 100 to 300 genes. So they've identified, they've kind of picked out in the germline the different syndromes or the different genes that are associated to the most common syndromes. So they do have the whole exome data, and when they usually it's matched. They do the tumor and the normal at the same time. So they're doing whole exome and RNA sequencing on the tumor, and they're doing whole exome on the germline, but only looking at certain genes in the germline. And then depending what you find in the tumor, they're going to unblock other genes in the germline to see if they're there also. So it's not a perfect gold standard.
I guess what I was trying to ask is, when they do this universal screening, screening? Are they just looking for everything? So are they picking up the BRCA ones? And the
They
other
are.
things? They are.
They are. And
So-
that's a big problem.
So then my
Yeah.
next question about the economic analysis is, how far does your planned economic analysis go? Are you taking into account the potential implications of finding that stuff on the universal testing?
Yeah.
Yeah.
Yeah, we are. Because it's so broad, we're really picking. So right now we've identified a clear scenario, like an osteosarcoma patient who is being tested for a specific gene and the risk of breast cancer. After that, we've made a specific scenario to troubleshoot a lot of these different things and techniques. But the goal is, after that, once the platform is made, then you can put in a lot of different scenarios and incorporating those incidental findings that you find. Because there's the concept of incidental findings in genetics, but then there's the concept of incidental findings in surveillance. If we're doing surveillance and then we find things that need biopsies and then don't need anything after, that's also a component. So it's very large. This is not going to be like a one person, one team thing, but we do want to build the framework to add on scenarios as much as we can.
Excellent. We'll move on to George, because
Thank you.
we still like it.
Okay.
That's really good.
Thank you.
Now it's on. The green light has appeared. And I gotta get this to work somehow. So my lab studies a disease called aortic stenosis, and I'll talk a little bit about why we're studying that. Talk very little bit about our sort of first discovery, which I guess is why Goudie says that I'm famous, but I don't know. I'm just guessing. And then we'll talk about what we're working on now. And it's good to see Suzanne here, because we're actually now we're deep into nutrition, Suzanne. So maybe I'll need your input. So aortic stenosis is actually the most prevalent valve disease in actually North America. The aortic valve, as you can see here, is a tri-leaflet structure. It's very pliable, and the leaflets are usually very thin. And over time, they become calcific and fibrotic, and it just doesn't open very well. And as you can imagine, this is the major valve that blood flows out of to go to all the other organs. So it's kind of critical. When it gets stenotic, patients become very symptomatic very quickly. And up until maybe in the last 10 years, the only treatment was actually surgery, where we had to actually operate on individuals to replace a valve. And more recently now, we can do this sort of like in a minimally invasive way, where we can still sort of replace the valve, but it's still a large procedure with a lot of morbidity and mortality. Patients are generally very old when they have this surgery, and often they actually can't have the procedure because they're so old. So one of the key things, and I think one of the things that has changed, is aortic stenosis, like a lot of disease of aging, has just been thought to be just disease of aging. So you get old and things start to degenerate, and that's a term that we use a lot, degenerative. But we're really realizing that it's actually an active process, and there's things you can actually do to prevent this process. And because of this sort of old thinking of degeneration, there's been no medical therapy for this condition. So basically we're in 2019, and we have absolutely nothing to do for these patients other than crack open their chest and remove their valves. There's no medical therapy we can do to actually slow this progress. And there's been a few clinical trials, they've all failed, and that's basically because we don't really know why the valve calcifies. So this is our first study. This is back when I had just arrived at McGill. It was building on work that I had done during my postdoctoral fellowship. And we actually performed this very large-scale study of valvular calcification and aortic stenosis. And we identified actually a variant in gene called LPA. I'll just talk a little bit about aortic valve calcium because I'm going to bring it up again. And aortic valve calcium is basically, by CT scan, we can actually take pictures of the heart, and we can actually pick out. Is there a laser on this? Yeah. So you can pick out these little flecks of calcium on the valve, and these flecks are early forms of the disease, where, as you can see, over time they progress to more calcium and more calcium, and as this continues, the valve basically becomes full of calcium and then just doesn't move. So one of the interesting things is we can actually study this as well, and what's interesting about this is you can actually start studying it in younger people. So in middle age, some of us already start to develop calcium, and people who develop calcium in middle age tend to be the ones who also progress to actual valve stenosis. So we've been working on this new cohort. Actually, one of the things I did when I arrived here is I actually went out of my way to try to find how do you get started as a genetic researcher, early investigator. So you need thousands, hundreds of thousands of patients. So I asked around colleagues, networking, who has data for sale. and then interestingly enough, there's always a place in the US that will sell you something. So the Kaiser Permanente group actually had this program where they had collected 100,000 individuals, and all from the Kaiser Permanente health organization, and they had all the data, sort of like the stuff that we often do here with using RAM-Q and administrative data and stuff I had actually done in the past. During my master's, using this stuff, I said, well, we can combine this idea of using administrative data with the fact that they had collected all these individuals and actually had genotypes already done. So just to give you an idea, if I had to genotype 100,000 individuals at about $150 a pop, this data set would be like several millions of dollars. I bought it for 50 grand. Good deal. That's what I thought. Yeah. So basically, using this, we were able to develop a case control study for aortic stenosis using the ICD coding, using the procedures that were recorded in the data set, and we ended up having about 44,000 individuals. We restricted to 55 years or older because that's really when we start seeing the disease start to appear. And so we had about 44,000 individuals with about 3,700 cases of aortic stenosis. So instantly, we actually had the largest case control study of aortic stenosis with genetic data when we got this data set. The first thing we did is, as I mentioned to you, we had previously published our big discovery at LPA, and the first thing we did, I remember I had an undergrad. So a lot of undergrads in my lab are computer science, do bachelors in computer science. So he understood nothing about this. All I told him was, I said, go into the data set and tell me if the RS104 SNP, which is the one that has been associated with AS in the past, do we see it? Because if we don't see it, I've just wasted 50 grand because it's obviously a garbage data set if we don't see what we're supposed to see. It's like a positive control. And I still remember he ran to the computer and he started typing all these things, and he goes, we don't see it. I was like, no, you can't be serious. And he's like, yeah, we don't see it. And then he goes, oh, wait a second, I inverted two of the numbers. So yeah, so that actually, so that's this is our sort of our replication cohort where we actually took our new data set and looked again for this LPA variant and showed it in this very large data set that it was also strongly associated with the development of aortic stenosis. So now we have this cohort. We've actually sort of validated it with a known finding that actually everyone sees now. Actually, we first described it, and now everyone who's looked for this variant in aortic stenosis sees it. So there's been meta-analyses all across the world. So it's very, very robust finding. So we know that our data set, actually, the fact that we were able to replicate that works. So now the question is, good, what else can we find? What else can we identify with aortic stenosis? So just because I know maybe not everyone is familiar with GWAS, what this is basically we've taken every single area of variation in the genome, and we've actually tested them with the presence of aortic stenosis. So basically what this is basically the p-value represents the difference between the prevalence of this variant in people with aortic stenosis versus people who don't have aortic stenosis. And basically we repeat this test at every single location on the genome that's known to vary. So in this case, what you're looking at here is about 300,000 sites. We can do much larger types of this kind of study, which we're actually in the process of doing now, where we can actually look at several million. But this is actually just looking at about 300,000 variants. And of course, the strength of the association is here on the y-axis, and you can clearly see that the LPA, which is what we've previously shown, is screamingly positive in this new data set, and we were intrigued by this. So it was not nearly, so just because you're doing all these tests, and obviously there is some statistical expertise in this room, you have to test, you have to sort of correct for the multiple hypothesis testing. So because you're now doing hundreds and thousands of these tests, now your p-value is no longer 0.05. That's meaningless in this kind of a data set. So in order to be very stringent, we actually use 5 times 10 to the negative 8. So that's where you determine that your result is actually significant. And as you can see, our previous finding is very, very significant as expected. We had nothing else in that range. It's kind of disappointing. I was like, oh, okay, well, that's not great. Nothing else to report. But you know, when you're an early investigator, you sort of like grasping for straws. You're like, okay, well, what's our next best option? How about this? It's sort of in the 10 to the negative 6 in genetics is considered like suggestive. So I was like, okay, what is it? Is it interesting? Should we actually work on this? Is this something that we want to pursue? Certainly statistically, it sounds like there's something there. So what is it? So it turns out that when you actually look at that specific variant, it actually happens to be this variant here, which obviously means nothing to anybody, which is fine. But what that lets you do is it lets you find out where you are in the genome, and you end up in a gene called FADS, so fatty acid desaturase synthase. So the minute when I heard that, I was like, fatty acids? That sounds cool. Maybe there's fatty acids, important in health, nutrition, this and that. I'm like, if there's actually a nutritional story behind aortic stenosis, we've now gone from a degenerative disease of aging to perhaps something that has a nutritional component, which obviously you can intervene on pretty simply because you can change someone's diet. So it's really, really, sorry?
That's less simple.
Yeah, well, that's true. That's true. Yeah, exactly. So this is what FADS does. So now we're going back to biochemistry. So FADS, there's actually, so this it's a locus. There's two enzymes that are encoded, FADS2 and FADS1. And if you remember your basic biochemistry, you have actually two parallel pathways. These are called the omega-6 fatty acids and the omega-3 fatty acids. Omega-3 fatty acids are the good ones, the ones that you get in the fish, and that's what you find in fish, EPA. You can actually eat alpha-linolenic, actually there's a spelling error, it's actually alpha-linolenic acid, which is an essential fatty acid, so you can only get this in through diet. And this is why you're supposed to eat a lot of flaxseed and other things, because this is where all the alpha-linolenic acid is. And this gets actually converted to EPA. Then you also have these fatty acids, or the omega-6, which people don't really know if they're good for you or bad for you. A lot of people think, oh, all polyunsaturated fatty acids are good for you. But there's been some debate about omega-6 because linoleic acid, which is actually found in a lot of like oils, corn oils, and there's a lot of discussion as to whether there's too much of those oils in processed foods. One of the things that makes this concerning is that when it does go through these conversion, it ends up producing arachidonic acid, which is like pro-inflammatory. So the question is it that there's, if you eat too much linoleic acid and you end up producing too much arachidonic acid, could that be bad for health? And this is a huge debate in the nutrition field as to whether all polyunsaturated fatty acids are good or not. We definitely know that these ones are good, but whether these ones are good is not so clear. Regardless, cool place to be for aortic stenosis. So the first question we asked ourselves is, FADS has been associated with a bunch of different risk factors. And of course, it was just associated with like cholesterol or one of these things. If that was the sort of the mechanism, I'd be kind of like, okay, whatever, not so interesting, more of what's already known. So the first thing we did as good epidemiologists, so we took our result. So this is our result. It was about a 13% decrease when you had the minor allele of this variant. And so that's the more rare version. So you had a 13% decrease, and then we actually adjusted for dyslipidemia, which is one of the things that FADS has been associated with, and there was not really much attenuation. And then we just said, okay, what about everything? All the cardiovascular risk factors, blood pressure, body mass index, diabetes, everything, and nothing really changed in the estimate. So that was interesting. That meant that this wasn't working through sort of typical risk factors. So now the big question is it worth pursuing? Remember, 10 to the -6, not so exciting statistically. I know it's exciting for some people in the room, but it's really not exciting for us at all. And then the question is, what in genetics, it's very common to find yourself, with a false positive, and you end up having to sort of, waste a lot of time. So the first thing we did after this is we said, do we have another data set sitting on our computer somewhere? And of course, I had just done a fellowship on that other data set where we made the LPA discovery. So we said, let's go look there to see if FADS1 is associated with aortic valve calcium, not aortic stenosis. So this is the preceding, this is the sort of subclinical, everyone's healthy, some of you in the room have valve calcium. Is it associated? And we were like, and then this is where like, big shock, oh my God, it's like identical. Okay, so now it has the exact same effect when you look at younger people with valve calcium. So it seems to be protective of developing valve calcium, and it also seems to be protecting people from developing an aortic stenosis.
Is calcium quantified, or is it
Yes, no. Yeah, we use yes, no because it's just simpler. But there are ways to do it. We didn't actually look at whether the quantified calcium. So then the big question is, can we really replicate this to the point where it actually becomes a robust association genetically? So we contacted colleagues around the world, and we said, and this is what's great about genetics. Everyone collaborates. People say, I kind of think of genetics a little bit like, it seems like the astronomers do this. It's sort of like we see something over in this part of space. Can you look there too? It's something funny. And then they all turn their microscope, their telescopes to that area, and they're like, yeah, we see it also. So it's very similar to that. We contacted a bunch of our colleagues in Quebec City, which are one of the leaders in aortic stenosis, in our colleagues in Sweden. Vanderbilt is the BioView cohort. UK Biobank now is available publicly, but we had a collaborator in Oxford who had access to that. UPenn, Epic Norfolk, which is a big epidemiological study, which now has sort of gone genetic. And there's also a small cohort in Umeå in Sweden as well. And through that collaboration, we ended up with 9,000 AS cases, which is just, AS is actually really rare. So bringing up, actually having data on 9,000 aortic stenosis cases is great. Controls now are easy to find because of UK Biobank. There's like hundreds of thousands of controls. But the case number is really what what limits you. So now we had 9,000 cases. And this is the meta-analysis. So it was actually really nice to see that when we started looking at the bigger cohorts, Quebec saw it, Malmo also saw it, BioView saw it, UK Biobank saw it, UPenn kind of saw it, and then of course other cohorts got really small, 400. The comment will get really wide, and the odds ratios kind of go a little funny. But when we look at the heterogeneity, there's 0. So it's like it's very, very consistent. And then when we pool it all, we end up with a p-value of 2 × 10⁻⁸. So we've actually achieved genome-wide significance. This is a real robust genetic finding. So we've been able to show that a mutation in the DNA somehow leads to aortic stenosis. In this case, it's the minor allele, so it actually protects from aortic stenosis. Big question is how, and now we can start thinking about mechanisms, because now we know our genetic finding is real. Question is now, how does it work, and does it have something to do with this pathway? So one of the nice things is that we know that that variant actually affects the expression of these two enzymes. So if you have the minor allele, which is the more rare version, you actually have more FADS1 and less FADS2. But what we also know is that the net effect of more FADS1 and less FADS2 is actually, for that minor allele, you end up with less arachidonic acid and less EPA when you actually look, because you get less conversion when you have the minor allele. So the sort of the people with the sort of variant have a less functioning pathway, so they don't produce as much. Which would actually be interesting, because which actually suggests that if this is true, that this is actually a bad pathway, and less of it associates with less aortic stenosis, that actually suggests that there's something maybe here that is causing aortic stenosis, and maybe it is that this pro-inflammatory product here actually happens to affect the valve. So one of the great things is having worked in Framingham and all these big US cohorts is that they've measured basically everything on everybody. So we call them and we say, do you have linoleic acid and arachidonic acid measured in your participants? And they're like, of course we do. And how many? Several thousand. Okay? So of course they already have aortic valve calcium, as I showed you. We actually had that data. So we said, okay, let's see whether the different fatty acids, how do they associate with arachidonic acid, with aortic valve calcium. So in Framingham, we showed that there was a suggestive association with higher arachidonic acid. This is actually log transformed. And also the arachidonic acid to linoleic acid ratio actually is the best measure of the flow through the pathway, right? So it's actually giving us an indication of how much flow is going through the pathway. And that was even more strongly associated to the development of valve calcification. And we also want, like I said, they're parallel pathways. So the question is, is it N6 or N3? So we also looked at the N3, and what we noticed is that the N3s, which is where we thought maybe we'd see, because N3s are known to be involved in health, we actually saw absolutely nothing with the N3 fatty acids. So again, being a geneticist, I never like to see something just once, because it might be wrong. So call up friends in Mesa and ask them, can you do the same thing? Of course we've got that measured. We wouldn't let the Framingham people have it alone, so we have it also. So when we look at arachidonic acid in Mesa, and honestly, when we saw these results, I said to our PhD student, I'm like, are you sure you didn't like fudge these results? Because like this is not just replication, this is like a mirror. So they saw a 14% increase per log transformed arachidonic acid unit, and a 22% increase for the ratio. And again, nothing to write home about for N3. And of course, when we pool them, the results become extremely strong for the N6 fatty acids and sort of the desaturation of N6 fatty acids to arachidonic acid, but absolutely nothing for the omega-6, omega-3 fatty acids. So what we've been able to show is at least that arachidonic acid measured in plasma is associated with aortic valve calcium, and it seems to be a reproducible biomarker. So we don't know exactly what is it causal or what, but it suggests that people who have more arachidonic acid, and certainly more of the ratio, seem to have a greater propensity to have valve calcium on their leaflet. But the big question is, does excess production of arachidonic acid cause aortic stenosis? Okay, so that's really what we want to know, and the key word here being cause. And as in genetics, we like to think of things that are causal. And this brings us to the idea of doing Mendelian randomization. For those of you who don't know, you've all heard of a randomized controlled trial where you take individuals and they get randomized to an intervention. Of course, that's usually a drug or placebo, and the drug usually has some impact on a risk factor that you can monitor, let's say cholesterol. So cholesterol goes down on the drug, and the placebo people have no change in their cholesterol. And then you can compare what happens to people. And because this is randomized and you know what you've done, you actually know that this is causal. So whatever happened here, the difference in outcomes is due to the drug, and it's due to the effect on the marker you were interested in. What's interesting is Mendelian randomization sort of takes advantage of the natural randomization that occurs at conception. So we're actually all sort of randomized experiments to a certain degree. And as opposed to using a drug to make these changes, we can actually look at individual genotypes. So there are people who have, for example, an allele that causes a decrease in a given risk factor. And then you can take people who have sort of the wild type or common allele, and they don't have any change. They have average levels of that risk factor. And you can do the exact same idea. You can just compare outcomes. But again, because these are randomized, the difference in the outcomes have to be due to this change in the risk factor. So that's the whole concept of Mendelian randomization, and it allows you to kind of get a sense of causality using this idea of genetics. So the big question is, can we do that with arachidonic acid? So what we do here is basically look at every single variant in the genome that actually produces or changes arachidonic acid levels. Remember, so there are genetic changes that affect arachidonic acid levels. And what you see here is that you see that and then we take each of those, and we see for each of those variants, we check the effect on development of aortic stenosis. So as you can see, there's a whole bunch of different variants that have different effects on arachidonic acid. And then we actually regress, we'll put a regression line through here. And basically what we're looking for to see is there a trend between variants that lead to higher arachidonic acid and more aortic stenosis, and those who lead to less arachidonic acid have less aortic stenosis. And again, it's genetic, and therefore, as you can see, it's a weak trend, but it's a trend nonetheless. And this is actually a statistically significant trend, which again makes the case that what you're seeing here is a causal effect of arachidonic acid. So basically, any way we change arachidonic acid in the body seems to also trend to having more aortic stenosis. And these are all genetic. So it's not what you ate. It's not whether you exercise. It's not what you're doing. It's actually what your genes are predisposing you to, and therefore the outcome is a change in the predisposition to aortic stenosis. So again, this is where it gets a little bit complicated. There's a whole bunch of different sensitivity analyses we usually run to show that these are robust. And here we've done it both for aortic stenosis and aortic valve calcium. These are completely separate data sets. That initial result is this one here. You can see it's a very strong result. We also see the same result for aortic valve calcium. And then when we actually do different types of sensitivity, where we exclude our top hit, results are attenuated but still pretty consistent with an effect. We do all kinds of different type of other approaches and with different assumptions, and we basically see here that no matter what we do, the result pretty much stays, except this technique, which is a really sort of like the extreme assumption, where you basically say it's all genetic. And the big problem here, as you can see, is that it's a very underpowered, especially when you're dealing with these small effect sizes, it's very underpowered. So really, that one becomes a little bit indeterminate as to whether there's a true effect. But everything else is very consistent, and it's also very consistent for aortic valve calcium. So the results are at least suggestive, definitely not definitive, but at least suggestive that the arachidonic acid component is actually causal in developing aortic stenosis. And it's really interesting because arachidonic acid, as you know, it can go into a number of different pathways, but leukotrienes is one of the main ones that it actually can be metabolized to, and there's actually been some studies showing that certain leukotrienes, when they look at tissue, the amount of leukotriene in resected valves correlates very well to the amount of calcium they have on the valve. So again, is that the final mechanism? It's not entirely sure, but that's sort of it's suggestive that we're heading perhaps to that kind of pathway. So our final discovery is that the excess production of plasma arachidonic acid may, and we're using may because we still haven't been definitive, but certainly strongly suggestive, maybe a molecular cause for aortic stenosis. So this is where it becomes interesting, because now we have some interesting implications of this. One is we could try to find drugs that try to slow this pathway down, because remember, our variant is protective, and it actually reduces the effectiveness of those enzymes. So you could actually sort of mimic the variant by creating a drug that does the exact same thing as it, and then slow production of this. We know that even if we slow it, we don't seem to have any impact by reducing EPA, because we don't see any effect with that. So if we just slow it enough, we can actually have less arachidonic acid, maybe less aortic stenosis, and perhaps even give that to someone who already developed some aortic stenosis, but late in their life, when they have just mild disease, we would then be able to prevent progression to more severe disease and avoid surgery and other things. The other thing that's really interesting, of course, is we could maybe decrease the amount of linoleic acid we eat, and that just would mean, unfortunately, we'd have to avoid the Twinkies and the processed foods that are very rich in this. Or perhaps it's interesting. This enzyme, as you can see, has a natural inhibitor, which is alpha-linoleic acid. So perhaps if you increase the amount of flax seeds and other things, you could perhaps shunt the enzyme to using a lot of N3 and less N6, and that would provide a potential dietary intervention to prevent aortic stenosis. So the key thing is that we've gone from a disease that's degenerative, that has no therapy, that we're like, we don't know why it happens, it's because you're old, to perhaps something that we actually have full control for. Now, as people pointed out, diet might be the difficult thing to change, but it is still under our control. So I didn't talk much about LPA, but we've shown that LPA is a genetic risk factor and promising therapeutic target, and now we're showing that FADS is also an interesting target, and that the omega-6 fatty acids specifically may be causal for valve calcification. This is now all our collaborators, and now we're actually what we haven't done. I just showed you the result of one variant from our GERA cohort. Now what we can do is actually everybody's doing a GWAS. Actually, everybody's already done a GWAS. They've actually all sent us their GWAS. So we're actually doing a meta-GWAS across all these cohorts to see whether there are more things. I can tell you we've actually identified about 20 new genetic variants associated with aortic stenosis. So with that, I'm going to just stop there. I want to thank James Engert, who's sort of co-lead in the lab, and all the work here was done by Hao Yu, which some of you might know. She's down on the second floor. She's our PhD student who's really amazing, going to be an amazing data scientist in the future, and really, her attention to detail is like beyond reproach. It's amazing. So congratulations to Hao Yu especially. Thank you. I always leave Ronald Fisher at the end, just to tell you why geneticists are a step ahead.
So thank you. That was super fascinating, and I can tell you that coming from me, who is like anti-genetic, That means something. Very, very interesting, very exciting stuff. This being child-adult rounds,
Yes.
and me being a pediatrician,
Right.
I was thinking the whole time, have you looked in children? Because, I wonder, is it really arachidonic acid that's causal, or is it just a marker for something developmental? And so it may be really interesting to look in children to see children who have aortic stenosis, which is very rare in children.
Yeah.
What kind of genetic abnormalities do they have?
Right.
I personally have a family, which I've always found very interesting, 2 brothers. One has Williams syndrome, which is associated with aortic stenosis.
Right.
The other does not.
Yes.
But he has coarctation, and they have other family members. I'm sure they would give you genetic material if you wanted it. But it may be worth looking.
Oh, yeah.
The other thing to look at maybe would be age of onset of the aortic stenosis and whether that is like a dose-response effect with your arachidonic acid levels. I just think there's like huge opportunity to learn something from the pediatric side to apply to this.
Yeah.
That could be really interesting in terms of developmental biology as well as outcomes in adults.
I mean, I think it's a great point. I mean, we haven't worked on developmental stuff, but actually the Quebec City group, which is actually sort of our friends and our competitors at the same time, have recently published a GWAS where they've identified a variant which actually appears to be almost entirely like mechanistically involved with probably developmental changes. It associates strongly to adult aortic stenosis, but also seems to associate with ASDs, VSDs, and other things. So there's no question that whole idea that there's developmental changes that can predispose to aortic stenosis, not just in children, but even perhaps in adulthood. It doesn't get seen in children, but it only
It's
leads.
like the fetal origins of adult disease.
Exactly. So and they're all there's actually the other huge area that sort of was the story maybe 10 years ago in this field was certain families, like you said, have aortic stenosis, and these are obviously very rare. Like they're like families where multiple people had early onset aortic stenosis, and they actually identified another developmental gene in those families, which seems to be very, very involved in early forms of calcification, not just at the valve, but elsewhere as well. So again, that whole idea of developmental effects leading to aortic stenosis is for sure an ongoing area of exploration. I think though that the FADs might have, for all we know, we don't know for sure, it might have. I think this is probably more a inflammatory as opposed to developmental, but we haven't looked to be 100% sure that there's no microscopic or other type of anatomical change at the level of the leaflets.
Yeah, we have tons of developmental biologists here.
For sure.
It would be worth talking, just asking.
Yeah,
Is
absolutely.
this something you've ever seen coming up in the developmental
Sure.
stuff? Because, like, ask Amy Ryan, she'll know.
Yeah, sure. It's interesting. The only other variant, the only other disease that this has been associated with is asthma. So this FADS is the only other. It's associated with a ton of different biochemical changes, as you could see, because it's very, very intimately involved in metabolism. But in terms of a disease, asthma is the only thing that it's previously been associated, at least at the genome-wide level, which again, pro-inflammatory, leukotriene type of picture. So yes, it's an interesting story.
But I think Beth's point is actually really, really important here. I know you're famous already.
But this is, either an opportunity to extend your fame further, because this is at one of our unique attributes.
Yeah.
And I know there is a pediatric cardiologist who does a lot of work in imaging, Gabriel Atit. I don't know if you've met him.
No.
Anyway, there may
Yeah.
be some younger investigators
Interesting.
who could
For sure.
could build on this.
Absolutely.
That's an excellent point,
Yeah,
and
yeah,
that's
yeah.
exactly the kind of thing we should talk.
Yeah, and we certainly have no collaborators at the pediatric level.
So that's your next project.
Yeah.
Next year's project.
Exactly.
I think
When
this
I-
was
when
one
I
of the
clone
most
myself, then I'll do
exciting
another- I'll do
child
pediatric.
adult health rounds we've had. So thank you to you both.